Over the last many years, we have seen many changes in the semiconductor advancements. We talk about films, but it is mainly made up of many atoms. We need to achieve a level of control by controlling each and every atom and each and every bond. ALD is a complementary set of reactions that grow films one atomic layer at a time. We will be covering the process of the atomic layer deposition, the advantages of this type of deposition, and applications. So the process. A first precursor gas is introduced into the process chamber and produces a monolayer of gas on the wafer surface. Then a second precursor of gas is introduced into the chamber, reacting with the first precursor to produce a monolayer of film on the wafer surface. So basically, these are the two fundamental mechanisms. Chemisorption saturation process, in which the first precursor gas saturates the entire first layer, and then the sequential surface chemical reaction process. Let's take an example of the ALD cycle for aluminium oxide, Al2O3. We have our trimethyl aluminium, that is the first precursor gas, introduced into the reaction chamber. The silicon surface substrate and the SiOH bonds. These are the hydroxyl groups, and this is the methyl group. The reaction taking place between the trimethyl aluminium and the wafer substrate. A hydrogen detaches itself from the OH and attaches itself to the methyl group, giving rise to methane, and the aluminium attaches itself to the oxygen. Now the surface is completely passivated. Trimethyl aluminium does not react with itself. This causes the perfect uniformity of ALD. The excess trimethyl aluminium is pumped away along with the methane reaction product. Now water vapor, that is the second precursor gas, is pulled into the reaction chamber. And the following reaction takes place. Two OH bonds are attached instead of the methyl bonds. And also it gives rise to methane again. Water vapor reacts with the dangling OH groups. And now the aluminium oxygen bonds are formed. The reaction product methane is pumped away, and the excess water vapor does not react with the hydroxyl surface groups. One cycle of ALD has been completed, and now these are waiting for a new pulse, for another layer. So the two reaction steps in a single cycle. The first precursor gas, trimethyl aluminium, and the second precursor gas, water vapor. So after 3 cycles, this is what you would get. The first layer, the second layer, and the third layer. Precursor requirements. It must be volatile and thermally stable. It should be preferably liquids and gases. It should chemisorb readily onto the surface. Short saturation time, good deposition rate, and gas phase reactions should not take place. It should not self-decompose, as it would affect the thickness uniformity. The precursor should not etch. We need uniformity at every layer. The type of ALD reactors: closed system chambers, open system chambers, semi-closed system chambers, semi-open system chambers. Here's an example of closed system chamber, which is the most common. The reaction chamber walls are designed to affect the transport of the precursors. As you see in the schematic, how the precursor gases are introduced and the end reaction product is exhausted out. The first precursor is pumped in through this high-speed valve onto this wafer substrate, silicon over here. And then the second precursor is introduced onto the wafer substrate again. The end reaction products are vacuum pumped out. The advantages: the thickness is determined simply by the number of deposition cycles. So the thickness is very precise. This can also be operated at very low temperatures. Gentle deposition process for sensitive substrate is an added feature for it. Applications: it has a wide range of applications. High K dielectrics for transistor gates in silicon, gallium arsenic, reduces the leakage current, faster switching speed, cooler transistors. After all, this is what we want from our modern transistors. The Al2O3 deposition is an example which we discuss right now, the aluminum oxide deposition. In DRAM transistors, using low temperature ALD oxide spaces gives a superior performance. The biomedical coatings possible. Nanostructures, conformal deposition is possible around and inside nanostructures. The UV blocking layers which are possible. And also the OLED passivation. Again, we have discussed the type of deposition for Al2O3. So these are the applications for the atomic layer deposition. Thank you.